determine the rate law from really experimental information. And that's usually how rate laws are determined. They're really determined experimentally. So remember that when we talk about our rate law, we're not talking about the rate expression that we talked about earlier, but we are talking about sort of this little generic sort of equation here, a to the x and b to the y. A reminder that this x, for example, and the y here, these are what are referred to as orders, and they are found experimentally, like we've been talking about. So they are not, though, they are not the coefficients in the balance equation, although they may end up being the same number. That is, again, not how we really determine them. The way that we do determine them is, and usually in these problems, as we saw in a number of examples last time, you're given some type of data table. And in that data table, you have information, for example, about the concentration of A in this one, maybe the concentration of B. You have some initial rates given to you. And it may be maybe 3 experiments in that table, maybe 4 experiments, maybe a ton of experiments in that table. But we use that information to help us really determine those orders. We could do it a couple different ways, but most people opt for more of the mathematical approach to do that. And that's where we take sort of that equation that we saw, or that formula, I guess, that the rate of 2 over the rate of 1 equals k a to the x and b to the y, and k a to the x and b to the y. So as we saw last time, as we talked about, it's not necessarily you go to the table, you just take the first and second entry. The goal when you go to the sort of that table that they give you is to really find 2 entries in the table where one of the concentrations, for example, remains constant while the other one varies. And you basically could plug it into here, and that will allow you to get something, say, like 4 is equal to 2 to the x. And you could do something like x is equal to 2 in that case. As we talked about, you could do kind of the natural log of both sides if you like and divide it. That's one way you can do that if you can't just kind of look at it. Once you do that, then you kind of switch it around. You would then keep the other guy constant and really vary the first guy, for example. And that will allow you obviously to figure out the order for the other reactant as well. Once you figure out actual orders or numbers for these guys here, we could also figure out the overall order of the reaction by basically adding those together. Gives you the overall order. In addition, once you also get those completed sort of orders, you then can rearrange the completed rate law, and you can solve for K, where it looks something like the rate is equal to A to whatever you got there in terms of the number, and B in terms of the number as well for that order, whichever one you got there. At that point, also, as we talked about, you essentially can go into any one you like from the table, any entry from the table, and you can put it in here, and that will give you the value of the rate constant, which is our little k. You know, as we also sort of talked about the other day as well, what does all these sort of orders and stuff mean to each other? Again, it's really sort of like the proportion of each of those reactants that you need to sort of have to establish a certain rate. We also saw just from our calculations last time that, when we do figure out something like, say the rate is k times a to the 1 and b to the 1 as well. This allows us to understand sort of, by changing, say, one of the concentrations, how it affects the rate. So like we did a pretty simple example, we just kind of put 1 in for the rate constant. If we had 2 molar there for our first guy and 2 molar for B, we would obviously get a rate of 4 molar seconds. In this case, though, if we decided to double this guy's concentration, we would have 1 again just for our imaginary rate constant, our 2 molar. And if we double the concentration, it would be 4 molar. And what we end up with is 8 molar seconds. So what this tells us is by doubling in this situation, B, we can increase the rate by 2-fold. And vice versa, if you decrease the concentration by half, you will obviously cut the rate in half. And again, you could kind of do that sort of relationship. And sometimes it's just easier to use, regular numbers. So you could kind of just, kind of visualize what's happening here. So again, if we had something where it was, say, squared, and we did our sort of same situation there, and we had 2 molar squared, this here is going to get us 2 squared is 4. 4 times 2 is 8 molar seconds for the rate. And again, if we decided to double that guy that's actually squared, how that would affect the concentration. So if we want 4 squared, that's going to be 16. 16 times 2 there is 32. We will actually end up with 32 molar seconds. So again, in this case, by doubling the concentration, because the order is 2, we obviously go up by a factor of 4 in this case, in terms of the rate. So, that's sort of what those orders sort of represent. If you just want to think about it in a basic sense, it's really sort of the proportion of how they react with each other. And it also allows you to think about, if I want to maybe speed up this reaction, should I add more of this guy? If I want to slow the reaction, should I add or take away some of this guy? And we even saw one, I think we had one where there was a 0, where obviously because it was 0, it would have no effect on it. So for example, if this was 0 order, you could do whatever you want to this. This is always going to become 1 and it will have no effect. Any questions on that stuff that we talked about last time there? Okay, so let us continue. So we did that example there. So now what we're going to talk about is actual kind of specific orders of reactions or overall orders of reactions and sort of what is taking place with these guys. And the first type of reaction we're going to talk about is first order reaction. And in a first order reaction, get a couple of things going here. That is A that goes to products. I really need to fix my arrows. I did something, they all got all crazy. So this is A that goes to product here. And we could write our rate expression for that, where we have minus the change in concentration of A over the change in time. Again, as we talked about earlier, again, it's a reactant, so we would expect it to be decreasing. We could go with the rate law here for this particular reaction. The rate would equal K times the concentration of A. And if we rearrange and solve for the units associated with K, we see that the units associated with the rate constant for a first order reaction is basically reciprocal seconds. It really doesn't have to be necessarily seconds. It could be 1 over minutes, 1 over hours, 1 over days, 1 over weeks, whatever you like. But it's usually some unit of 1 over time. A lot of times we think about it as 1 over seconds or reciprocal seconds, because when you do, for example, an experiment in the laboratory, most of the time you're not going to be sitting there for days doing the experiment. So a lot of times these reactions occur relatively quickly when we do them in lab. And a lot of times we sort of measure time in seconds. So that's a very common unit. But again, just to remind you, it does not necessarily have to be seconds, but it does have to be some unit of time. So a reciprocal second, reciprocal unit of time is an indication that you're dealing with a first order. Why is this important? As I maybe talked about the other day, it's important because there will be a lot of problems where, they will not put like flashing lights on the problem and go, hey, we are now dealing with a first order reaction. They will give you pretty much the rate constant and the units that are associated with the rate constant. And from you just seeing sort of the units that are associated with that rate constant, you should be able to determine sort of the order of the reaction. So it's important to understand that when you see certain units associated with K, it will also tell you the type of reaction that you're dealing with. Why is that important? Well, first order reactions have specific sort of equations that you use. to determine things like the change in concentration over time and stuff like that. So sort of a concentration time-dependent equation. There's a specific one that's used specifically for first order. So let's take a look at a couple of graphs, though. These are a couple of graphs that are also commonly associated with first order. On the Y, we have concentration. On the T, we have time. And what we see here is what we would expect. As time progresses, we are decreasing the amount of A, or the reactants, and that's what we would obviously expect to happen as products are going to be formed. Now, most of the time, people will take this rate law and sort of do what is sometimes referred to as an integrated rate law, and it will end up with this guy right here. And that equation right there is specific for first order. That is the natural log of A is equal to the natural log of A naught minus KT. So what are some of these guys? Well, A is sort of, if you want to think about it, your final concentration. A naught with the little zero there on the bottom is the initial concentration. K is our rate constant. And sometimes people mess up with T here is actually time, not temperature. So that's lowercase t, and it is time, not temperature. This is the equation that we use for first order to basically determine, what's going to happen with concentration if we perhaps have something run for a particular period of time, or if we have the final initial concentration, how long it would take to do that, sort of the time dependency. There's also, as we will see, a half-life equation for first order, which is the natural log of 2 divided by K, or 0.693 divided by K. Natural log of 2 is where 0.693 comes from. So these two equations actually a lot of times will have to be used, or sometimes will have to be used together. So a lot of times, you'll sort of have to use these guys together. Maybe you have everything for this equation except for like the rate constant, but they give you the half-life. So a lot of times, very commonly, you could use the half-life equation to figure out the rate constant. What does half-life mean? Well, as we'll see in just a bit here as well, the half-life basically means the time it takes for half of whatever you started with to kind of go away. So you started with 10, obviously after the first half-life, you end up with 5. After the second half-life, you end up with 2.5. And after that, I need a calculator, but you keep dividing by 2. And that's basically what half-life is. So with this original equation here that's in this box, if we actually rearrange this equation and rearrange it like this, we get the natural log of A is equal to minus KT plus the natural log of A naught. And what that is rearranged in the form of is actually a straight line, which is a very common theme when we're doing kinetics. Is we like to graph things as a straight line, and this is y is equal to mx plus b. And just in case you're not sure what all that means, let's just make sure. What that means is basically when we go to make a plot on the y, we should plot the natural log of A, which is what we see in this graph. On the x, we should plot t, which is time, which is what we see here. And if we do that, we should really yield a straight line where the slope of that line would equal minus k, which is what we see here. The slope equals minus k in this case because if you look at this line, that line is a negative slope. So the negative slope and the negative k will turn your rate constant into a positive value for k. Again, because that line has a negative slope, it would obviously give you a negative value for the slope. And then when you times that by negative k, that turns that into a positive value for the rate constant. So that's an important thing to keep in mind, especially as we come up on some labs coming up in the next couple of weeks or few weeks. When you actually do the graphs and you figure out what k is, k should probably be a positive number. Any questions on that so far? So definitely important things here in terms of this slide. Let's go with where we at there. Definitely knowing this equation. Definitely knowing the half-life equation, which we'll see again in a second. Also knowing that the units associated with K are reciprocal seconds is really important. And knowing these two graphs, to be truthfully honest with you, out of these two graphs, this one over here is really the one that is mostly associated with a first order graph. This one is as well, but we will actually see the graph on the left again a little bit later. But definitely the one on the right is usually the graph that most people associate with a first order graph. But really the one on the left still is a first order graph, so you should be aware of it. But the difference again between these two graphs is the one on the left is not a linear relationship. The one on the right is a linear relationship. So that's an important distinction between those two. Any questions on that there? So again, here's a, excuse me, an equation here, and we do have our reaction here. And you can see if we do plot, obviously, the natural log of our concentration and time, we do yield our nice kind of straight line where we could figure out the slope old school by picking 2 points that are on the line and take the change in y over the change in x. And that would allow us to graphically figure out the rate constant for this. All right, so why don't you take a second here? We have this reaction which goes from 2A to B is first order with a rate constant of 2.8. How long will it take for A to decrease from 0.88 molar to 0.14 molar? So take a minute or two and see what you come up with, then we'll talk about it. Okay, so let's take a look here and see. So they were nice enough to tell us in this particular one that this is first order. Again, if they did not tell us it was first order, we would actually know it is first order, again, based off of the units that we see here associated with the rate constant. So that rate constant has reciprocal seconds, which tells us it definitely is first order. And that also should then tell you we're looking at sort of what's happening with time and concentration changes. We want to use that integrated rate law for first order, which is the natural log of A equals the natural log of A naught minus KT. Here in this particular case, we have K given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. My initial concentration here is going to be 0.88 molar. My final concentration here is going to be 0.14 molar. So that is everything we need to solve for T. So that would give us the natural log of our final, which is 0.14 molar, equals the natural log of 0.88 minus K, 2.8 times 10 to the minus 2 reciprocal seconds equals time. I personally take the natural log of 0.14. I then subtract the natural log of 0.88 to do that. So natural log of 0.14 equals minus the natural log, if I hit the right button there, natural log of 0.88. And if you do that, you're going to end up with like a minus 1.838 on the left-hand side equals minus 2.8 times 10 to the minus 2 reciprocal seconds. We're then going to divide this to the other side. And when we do that, we end up with about 66 seconds, give or take. Again, the negative here and the negative here are going to turn that into a positive number. It's reciprocal seconds. When we kind of move it over to the other side, becomes seconds up on top, and we end up with about 66 seconds for that to occur. Any questions on that map there? So again, they won't always tell you, right there in words, it's first order. You want to look for those little kind of keys to help you figure that out when we see, the units associated with the rate constant. Also really important when you're using this equation as well, we may see it along the way, or you may see it along the way, is, these two terms right here. Sometimes the time unit are different. So you might have maybe something in weeks and maybe something in days or something like that. So you always want to make sure, the units, and especially the time part of the units associated with K and the actual time are actually in the same units. So sometimes they are kind of different. So you want to watch out for that as well. So half-life, as I sort of mentioned earlier, is really the time it takes for half of whatever you started with basically to disappear. And specifically here for our first order reaction, the half-life is that natural log of 2 divided by K, which means the half-life here is dependent on the rate constant and not dependent on any type of concentration values there, just actual the rate constant, how fast it goes. So if we want to know what is the half-life of N2O5 if it decomposes at a rate constant of 5.7 times 10 to the minus 4, we basically can just go right into here and put in our number. So that would be the natural log of 2 divided by 5.7 times 10 to the minus 4 reciprocal seconds. And if we do that, it looks like we end up with something like, let's see here, natural log of 2 divided by 5.7 to the minus 4. Looks like we end up with something like 1,216 seconds is the units here with 2 sig figs. Might want to take that back down to 1,200 seconds, which is about 20 minutes, give or take. Any questions on that calculation there? Okay. Oh, and the bottom part of the question, which is obviously how do we know it's first order? We do know it's first order because of the units that we see here. These are reciprocal seconds for the rate constant. So again, that's a very important part to determining, what the order is. Here again, it's just a graphical representation of half-life. And as I mentioned, obviously you can see after every half-life, we pretty much lose half of what we started with. Normally, if you go about 10 half-lives, pretty much is all gone at that point. There's not very much left in this particular case here. And again, we can see the decrease over time as well as we look at it. If you ever needed to, figure out the half-life equation and you're not sure what it is, you could always mathematically solve for it by going into sort of these integrated rate laws. The difference is basically at the half-life, our final concentration would be that divided by 2, right? Our initial concentration divided by 2 would be substituted into here, and you can actually solve for T, and you'll eventually get to the half-life equation. In my practice, probably better just to kind of memorize it than try to derive it yourself, but you can, if you're good at math, sort of derive the half-life equation from the integrated rate law by doing that move right there. So why don't you take a look at this one here and see what you come up with. We have this reaction has a rate constant. Find the concentration of SO2Cl2 at 865 seconds if our initial concentration is 0.0225. So take a couple of minutes here and see what you come up with, and we'll double check, make sure everybody's on the same page. To tell us that it was first order, we definitely can figure that out by looking at the units that we see associated here with the rate constant. And again, that does tell us it's first order. So because of that, we do want to think about our first order rate law here. So in this case, we're actually looking for what is concentration after a period of time. So we're looking for that guy. We do have our initial concentration given to us, which is basically 0.0225. We also have the rate constant given to us, which is 2.9 times 10 to the minus 4. And lastly, we do have how long we're going to do this for, which is 865 seconds. Now, because these two guys are together, as I was just mentioning before, we're going to be okay in terms of units here. They are both basically in seconds for the units of time. So again, you do want to keep an eye on that. Very commonly, they are going to be maybe in different units. So you don't want to get the wrong one. So basically, we have everything we need to kind of plug it in. So natural log of A is going to equal our natural log of our initial, which was 0.0225, minus our K, 2.9 times 10 to the minus 4, and our seconds, which is 865 seconds here. If we kind of clean up the right-hand side of the problem here, we're going to take the natural log of 0.0225. We're going to subtract it from 2.9 to the minus 4 times 865. That's going to give us something like minus 4.04508997. I didn't feel like rounding at that point. Hopefully you know, but just in case you don't, to get rid of the natural log over here, we pretty much need to take the E on your calculator there of both sides. When you take the E of this side, that just goes away basically, and we end up with A. And if you take the E of the other side there, we end up with 0.0175. It is a concentration, so we do need the molarity there. First off, any questions on that calculation?
Yes, Professor. I did not get that number on the right-hand side, the negative 4.04. I got negative 3,000 something, so I'm pretty off. I don't know what I did
Yeah,
wrong.
so again, if you doing this on this side, you might want to maybe do it in parts, if you will. So you might just want to do the natural log of the first number there, which was 0.225. And if you do that, that's the natural log of 0.0225. That gives you something like minus 3.794. Then you probably want to do the part here. Want to make sure you are using your exponent button. So make sure you go 2.9 and then hit your exponent button, hit your negative button, and 4, and then times it by 865. And if you do that, you should get, hopefully,
Yeah, I did it that way too, and I still got the same number. So I don't know. Should I include brackets maybe somewhere? Because I didn't
yeah,
do.
if you're gonna punch it all in at once, you might want to do brackets. So if you did it kind of parts like this, you
Uh-huh.
then could add subtract them together basically, or which is adding them basically in this case because they're both kind
Okay.
of negative, and you will get that minus 4.04485 number. So you might want to do it parts. If you're going to do it all together, you definitely should do brackets. So personally, on my calculator, I hit the natural log of 0.0225. I hit equals, and then I go subtract, and then I bracket it up with the numbers in the parentheses and hit equals. So you just want to kind of figure out which way to punch it in correctly, but definitely on a lot of calculators, you probably don't want to just punch it all in at once, maybe with no brackets anywhere, because you probably will get the wrong answer.
Okay. Thank you so much.
You're welcome. Because usually, again, if you kind of punch it all in at once with no brackets, what's going to do, oddly, is kind of like do the subtraction part here first, and then do the multiplication part while you really are doing the multiplication part first and then doing the subtraction second. And so that's why it's important, again, when you punch it in, that you kind of make sure either you do brackets or do it in part work or piecework, and you'll be okay. Other questions on that? Okay. The other thing that's important here is obviously, as we could see, the answer does make sense because we are decreasing with time. So our initial was 0.0225 molar. It did go down with time, obviously, as we see here. We ended up with 0.0175. So because that's obviously the reactant, if you did the calculation like this and you ended up with actually higher concentration than what you started with, definitely something is wrong. So, that's good ways to think about things, to kind of check to make sure everything's okay. Other questions on that? Action. So because this again is first order, we would want to use the one that's specific for first order. And basically in this case, we just need to plug and chug into here. And our reciprocal seconds will obviously come up on top once we do the division. And that would get us natural log of 2 divided by 0.271. Going to give us 2.56 seconds as our half-life, which is, if you think about it, pretty fast. So every basically 2.5 seconds, you're going to lose half of what you started with. So that's a very, very fast sort of reaction and half-life, right? It's going to basically disappear very, very quickly. By the time you get 20 seconds, you probably went through 10 half-lives, and it's probably almost gone at that point. Any questions at first order reactions? Again, by the way, to get a first order reaction, there's sort of one way to sort of achieve that. As we've been talking about, obviously the order for A would have to be 1. That's kind of like the only way to get that first order. It is possible to have a first order reaction where you have 2 reactants, where maybe A is first order and B is 0 order, right? So that's another way potentially you could do that. And obviously, as we've talked about earlier, that would obviously have no effect on the rate at that point, and that would also give you a first order reaction. So overall, those are kind of 2 ways you can sort of achieve a first order reaction. Have just one reactant where it kind of goes through like a decomposition reaction, for example, or it could have potentially 2 reactants where maybe one of them is 0 order, which really won't have an effect on the actual rate of the reaction. Any questions on that? Okay. So then let's talk about the next type of reaction we're going to talk about, which is second order reactions. And second order reactions are a little bit different than first order. Same in the sense that my arrow still is missing. A going that way. So when we do this, we get the same sort of arrangement here. The negative change in concentration of A over change in time. The rate would equal K times A squared, which is why it's second order overall. If we look at the units associated with a rate constant for a second order reaction, it is 1 over molar seconds. So 1 over molar seconds are molarity to the -1, seconds to the -1 is again the units that we typically see. Just like in first order, again, very common that the sort of unit of time here is seconds. Again, does not have to be seconds, just needs to be some unit of time. But as I mentioned earlier, most of the time we are doing sort of reactions that, are sort of timed in seconds. So it's a very common sort of unit. In addition, there is also an integrated rate law for a second order reaction, and that is 1 over A is equal to 1 over A naught plus KT. We also see that unlike the first order, a second order reaction has a different half-life, which is the half-life is equal to 1 over K times the initial concentration. So unlike first order, the initial concentration here has an effect on the half-life. So the amount you start with will have an effect on the half-life of that particular reaction. So, if we had, excuse me, a much higher sort of concentration, that's going to result in a sort of lower sort of half-life, as opposed to a smaller one that will have a greater half-life that would occur in that particular case. And again, you could just see that mathematically. For example, if we just think about the half-life here, let's just say that the rate constant here was 2, and we started with, say, 2 molar initially, right? If we do that, that's going to be basically 1 divided by 4, which is 0.25 would be our half-life. And if we did the same thing 1 to 2, and we started with 10 molar on the bottom there, that'd be 1 divided by 20, basically. And that is a half-life of 0.05. So you can see that, the smaller the concentration, the greater the half-life we're going to sort of have. The larger the initial concentration, the slower the half-life will be. And again, that makes sense, right? If you are starting with a smaller amount, every time you lose half is going to be kind of quicker. And if you're starting with a larger amount, it's going to take longer for you to kind of use it up. So having that initial concentration there affects basically the half-life as well. This equation here are all of our same sort of guys. So the first A there is kind of like the final concentration. The A naught is the initial concentration. K is our rate constant, and T is our time. We could also rearrange this equation like we did with our first order one. The 1 over A is equal to KT plus 1 over A naught. And when you rearrange it such as that, that is writing it in the form of a straight line, where this is y is equal to mx plus b. So same sort of theory as to what we normally see on the graph. On the y is the 1 over a. On the x is the t. And again, if we graph that, we will get a straight line, which is what we see here. We also see that straight line is a positive slope, and that means that the slope in this case actually will equal k here, the rate constant. So the slope of that line will equal k, and obviously the y-intercept would equal that guy. So just like kind of first order, there are a few important things, obviously, off of this slide that you need to know. So obviously the units associated with K. We also need to know the time and concentration reaction, our formula. You need to know the half-life associated with second order. And obviously you need to know the common graph that's associated here with second order. Again, yielding you a straight line. The only one typically we come across that yields you a straight line in the positive direction here. Also a reminder that this is plus, not minus in this particular one. A couple ways you could get to a second order reaction is what we see here. A is to the second order. You also could have A to the first order, and like B to the first order would give you an overall of second order reaction. So again, there's a couple different ways you could do that. Maybe one reactant that's sort of to the second order, or a reaction of two reactants where they're both first order. Any questions on that there? Okay, then the last type of sort of reaction we're going to talk about in terms of orders is a zero order. And again, we can do our reaction here. The rate would equal K to A to the 0. As we've been talking about, something to the 0 power is 1, which means the rate equals the rate constant. And what that means is the units associated with a zero order reaction is molarity over seconds, which is typically the units that we associate with the rate. We also have some integrated rate laws, some concentration versus time guys for a zero order. And here we go. We see this is our concentration versus time specifically for a zero order reaction. Same characters here. So our A is our final, A naught our initial, K is our rate constant, and T is our time. Also has a specific half-life equation in this particular case. And we also do see that the concentration up there affects the half-life. So again, if we just kind of do our simple math approach to see how that affects it, let's just say we started with 2 molar up on top, and let's just say that the K was 1, so we'll leave it at 2. That would give us a half-life of 1. If we doubled it, 4 molar up on top, and we had, say, our same 2 on the bottom, that would give us a half-life of 2. So doubling the initial concentration will make the half-life also double as well. So again, the effect of the initial concentration here on the half-life obviously affects how it behaves. This integrated rate law here is very similar to first order, other than the fact that there is no natural logs happening here. So we can also, much like the other two, rearrange this equation in this form. And this also is rearranging this guy in the form of a straight line. So this again is y is equal to mx plus b. So that tells us what we should be graphing here. On the y should be our concentration. On the x should be our time. Again, should yield you a straight line, which it does. Also a negative slope happening with that line, which is why the slope is equal to minus k, which is what we see here. So that is the typical graph that is associated with zero order. And this is the graph which you do not want to confuse with the graph we saw earlier, which was also the concentration of A versus time. The difference is that did not give us a linear relationship. It gave us with that decrease over time, and that is first order. So these are the same graphs that are happening, but the difference is when you graph concentration versus time and you yield a straight line, you're probably dealing with a zero order reaction. If you do concentration versus time and you get this decreasing graph here, not a linear relationship, you're probably dealing with something that is first order. So again, these are two of the same graphs, but they are showing you something different when you look at them. Any questions on that there? So just like the sort of other one here, we want to, off of this guy, make sure that we know, again, the units, the specific concentration time equation there for zero order, obviously the half-life equation that goes with that, and obviously the graph and what it looks like there that's associated with a zero order reaction. Any questions on that particular one there? Okay, so why don't you try one here? The reaction Q goes to 2R is second order. Initial concentration is 0.01. After 5 times 2 seconds, Q is equal to 0.001. What is the value of the rate constant? So take a couple of minutes to see what you come up with. Typically, our second order formula here. Remember, it is plus and not minus KT. In this case, let's see here, we are given our initial concentration, which is 0.01. We're given our final concentration, which is 0.001. And we do have our time, which is like 500 seconds, basically. And at this point, we have pretty much everything we need to put in here. So we got 1 over our final, which is 0. I wrote that backwards there. Huh? That's initial. That's final. 1 over 0.001 is equal to 1 over 0.01 plus our K, which is what we're looking for. And in this case, we do have got the 800 in my head, 500 seconds happening here. Again, mathematically here, sometimes it's best to kind of do these things in parts. So I do personally 1 divided by 0.001. I'm then going to subtract this guy to the other side. And when I do that, I can go minus parentheses 1 divided by 0.01. That's going to give me something like 900 on the left-hand side. And that's going to equal K times our 500 seconds, We're then going to divide 500 seconds to the other side here. These guys are going to cancel. And that will leave us with 1.8. And in terms of the units, again, obviously these are molarities on the bottom. So molarity is still there on the bottom, 1 over molar. And that means that we end up with 1 over molar seconds, which are the units that we do associate with a second order reaction. Question on that math there, or the problem, or any numbers came from, or anything? Okay. So again, it's important to make sure that you sort of rearrange these things correctly. Also important to make sure you don't forget about the units here at the end for anybody, and that you end up with the right ones. Any questions on first order, second order, or zero order reactions? Most of the time, those are the three probably common ones that we'll come across. And that's really because if you think about it, for example, we don't oftentimes have a lot of reactions that are like 3 or 4 different guys involved in terms of the reactant side. If we did have something like that and they were each like, say, first order, this would be like a fourth order reaction overall. And that's not very common. So a lot of times you think about reactions you deal with, a lot of times it's like 2 guys coming together. So maybe you got like a second order, maybe one of these are, by itself, 0, and you get a first order, or we have a decomposition reaction, which is very common. Occasionally, we do get, maybe 3 things together we react. But maybe one of these guys are 0 and the other ones are 1s, and you get like a second order reaction and stuff like that. So when we talk about sort of first order, sort of second order, and 0 order, those are sort of, I'd say, the common sort of types of reactions that we have, just based on how reactions come together. Any questions on that? Excuse me. Okay. So just to sort of reiterate the important things here of all these guys. These are obviously the important equation, the concentration versus time equations for each of these that you do need to know, and also the corresponding half-life equations. Again, if for some reason, you can't remember these things, but you are fairly okay with math, remember that you could sort of solve for the half-life equation by substituting that in for our final and solving for t, and that would get you these guys over here. Again, probably just better to memorize them so you know what they are. In addition to those, obviously, to remember graphically, which is a very common way as well that we sometimes try to determine the order of a reaction, we can use the specific graphs that we talked about to help us determine, what order of a reaction we're dealing with. Is it 0, first, or second order? And these are, again, our linear graphs that we're looking for. So a reminder that if you ended up doing a graph of the natural log of A versus time, and you got a straight line, you did a graph of 1 over A versus time, and you got a straight line. And if you did a graph of A versus time, and you got a straight line. These do represent, again, first order, second order, and 0 order. So right this way, 0 order reactions. Let's say you did all 3 graphs and you're trying to determine, which one is most linear. This is where we could use something like Excel or something like that, where we use that R squared value. That R squared value is that linear coefficient. The closer to 1, right, means that is most linear. So if you did all 3 of these graphs in something like Excel, XY scatter plot did like your best fit line, you would compare the R squared values for everybody, and whichever one had the one closest to 1 would be the most linear, and that would graphically tell you what the order of the reaction would be in that particular case. Any questions on that? Any questions? Okay. All right. So again, you do need to know those things. You need to know, again, the orders, the graphs, the equations, and obviously the half-life equations, and those units for K, super important. Any questions on any of that there? Okay. So next thing we're going to talk about is actually sort of energy and reactions and temperature and how it affects it. When we do a reaction happens in a couple of steps, as was badly shown here with this A, B. So if we have a reaction, we usually start out obviously with our reactants here, and we end up with our products. But there is a process that sort of occurs as we're going from reactants to products. So going from reactants to products, the reactants actually has to climb this hill basically to get to the other side. And as it's doing that, what is happening is the reactants are starting to break all their bonds. And as they get up here, they're starting to actually make some bonds. And then hopefully they kind of transition downward, to our products in that particular case. So a couple of things that's sort of important when we look at this relationship between reactants and products here on the left-hand side. The reactants are higher in energy than the products. So in order for our reactants to get down to our products in terms of energy, energy has to be given off in this particular case. And when we release energy, or energy is given off, that is what is known as a exothermic process, right? Exothermic processes are usually indicated with our enthalpy value that is negative, right, overall, for a particular reaction. Energy is being given off. Opposite is true here. If we kind of look over here, here's our reactants, here's our products. And our reactants in this case is actually lower in energy than our products, which means energy actually needs to be put in this reaction. So it needs to be absorbed. And when we absorb energy, that is what is known as a endothermic process. Again, in relationship to delta H, that's usually things that are positive. Also has a hill to climb. This hill that it has to climb is what is referred to as the activation energy, sometimes abbreviated as E of A. It is really the hill that those reactants has to climb to get to the other side. So it's that big hill it has to climb. That hill obviously would have an effect on how fast the reaction would occur, the rate of the reaction. If it's a small hill, then it probably would occur relatively quickly. If the hill's really big, it's going to take a lot longer to get to the other side, and the rate of that reaction probably will be a lot slower in that particular case. So what happens though, as we sort of approach the top? Well, when we approach the top up here, we get this guy here with the weird symbol next to it. This is what is sometimes referred to as a transition state complex, or sometimes referred to as a activated complex. And what it is, as I was mentioning before, it is something where we typically have, kind of bonds that are being broken, bonds that are being made. So we have these partially broken bonds. We have partially bonds that are being made. It really is, much like the name implies, a transition sort of happening at that point. We also see that this sort of intermediate here, or this transition state, happens at pretty much, in both cases, the peak of energy. So in both cases, that is essentially what we have when we sort of hit the highest point in terms of energy. As you may know, right, things in high energy are not very stable. Things don't really like to be in high energy. They're not very stable. And that's why a lot of times over the years, it's very hard to a lot of times isolate what we got going on here because this is so high in energy. It pretty much very quickly decides I'm going to head down the hill, basically, and it's going to head down the hill. Same thing here. Usually, fairly quickly, because this is very unstable, because of those partially made bonds, partially broken bonds, it decides it needs to kind of go down the hill very, very quickly. Um, and again, sometimes very hard to isolate that sort of species at the top there because of that high in energy and sort of instability. Any questions on that there? We also see that in our exothermic reaction, the activation energy or that hill is much smaller than in our endothermic process. Also, why perhaps this is endothermic, we need to give everybody a little bit of energy to kind of get up and over that hill, basically to get to the other side. Any questions on that there? Okay. So let's talk a little bit more about sort of this temperature and rate relationship. When we do change the temperature, it does change the rate of the rate law and how fast the reaction occurs, as we'll talk about. For the most part, usually if we increase that temperature, we usually will see an increase in the rate, and vice versa. If we decrease the temperature, usually we see sort of the rate will drop in most reactions. Again, the idea there is when you're increasing the temperature, you're putting more energy in. More energy means you have a lot more reactants that have enough energy really to get up and over that hill to the other side. Vice versa, if you sort of decrease the temperature, everybody has a little less energy. They're not going to have maybe as many guys that can get up and over to the other side. Uranus here has a relationship that basically describes that, and that is K, which is our rate constant equals A. A is a frequency factor. It is kind of the, again, proportion of molecules that sort of have enough energy to get up and over that hill to the other side. E of A is our activation energy. R is the gas constant, and in this application, it is not the one that we use for gas law. It is the one that we use when we're talking about energy. So it is the 8.314 version of the gas constant. T is our temperature, and much like everything in chemistry, should be in Kelvin in this particular case, so that everything cancels out, again, because we have Kelvin over here in our gas constant. We'll see a more sort of usable version of this equation in just a second, but that's sort of the non-integrated version of it. And again, here just graphically showing you, we have our reactants that essentially need to, all these bonds need to be broken. And then by the time it gets down here, obviously all these bonds need to be made. And again, we get that kind of transitioning happening as we go up the hill to the part where we got the guy with partially made bonds, partially broken bonds at the peak of the energy and going to come back down in terms of here. When we look at this graph here, we could know for sure I see reactants higher in energy than products. I know for sure that this is a exothermic diagram because of that. Again, exothermic, you will see your reactants higher in energy than your products, and vice versa for endothermic, your reactants will be lower in energy than your products will be higher in energy. So again, just the location of those two on a graph such as this gives you that information about what type of reaction you're dealing with. So a little bit more about that guy when we get to the top of the hill there, as I mentioned before, that activation energy is that hill that we've been seeing that they have to kind of climb to get to the other side. Again, at the very top there, you get what is referred to as that activated complex, our transition state complex. Years ago, they used to call that top of the hill the transition state. And again, this used to be called the transition state complex, but now sometimes people will call it the activated complex all the same thing. It's basically that species that's at the top of the hill there. Again, very high in energy, and as we talked about, very sort of unstable because of that high energy and those partially made bonds, partially broken bonds. You'll very quickly go to the other side. And this is sort of what we see here. For example, we start with this guy here, and although it doesn't change all that much, there is some repositioning of the carbon and the nitrogen that occurs in this process. So what happens is, again, the original guy here starts to basically weaken those bonds. These bonds start to break as the process occurs. And as you can see here, it's starting to break some of those bonds as it moves up the hill. It's also starting to make some partially bonds as well in that rearrangement that's happening. Remember here, the nitrogen started connected there to the CH3. We're now rotating it into the carbon being the guy attaching, again, dropping back down the hill where we do get the final sort of rotation that occurs. The change in energy that occurs, which is our delta H in this case, would be negative, as again, our reactants are higher in energy than our products, and that difference or the change in the enthalpy would result in a negative number. So again, you can see kind of starts, we start switching around the bonds, moving the bonds, breaking and making, and again, eventually re-ends at the end of the hill and its final proper sort of location. All right. So looking at that Uranus equation, this is typically the graph that we see associated with it when we graph the rate constant versus the temperature. And what we see is what we just were talking about. At higher temperatures, we have a much higher rate for that particular reaction, which means it occurs a lot faster, the rate constant. At lower temperatures, we see a very slower rate constant, which means that reaction would occur a lot slower. So taking this equation here and really taking the natural log through this equation here will get us this guy right here, which is the natural log of K is equal to minus E of A. The minus is kind of far over there. I'll move it over. Minus E of A over R 1 over T plus the natural log of A. So this equation here, I'll rewrite it just to make sure. It is minus E of A over R 1 over T plus the natural log of A. This is actually the equation written in the form, surprisingly enough, of a straight line. So this would be y is equal to mx plus b. So the typical sort of Uranus plot that we see is on the y, we have the natural log of k. On the x, we have 1 over the temperature in Kelvin. And the slope of that line will actually give us the activation energy or allow us to solve for the activation energy. So when we do that sort of graph, which is what this graph is showing, so this graph is showing what I just wrote there, that minus E of A over R 1 over T plus our natural log of A. This again, y is equal to mx plus b. You can see that we get a straight line when we do that graph. The slope of that line, if we pull it out from this equation, the slope is equal to minus E of A over R. Since R is a constant, 8.314 joules per Kelvin per mole, that means that by knowing the slope of the line, if we times it by the gas constant, we can figure out the activation energy from that. By the way, if you do that, the activation energy will be in units of joules. Usually activation energy is given in kilojoules, but if you do it through the graph here, it will end up in joules because of that. Also important to note, if you look at this line here that you typically get when you make this graph, that is a line with a negative slope, which means that this number is going to be negative. We have the negative here. That's important because the activation energy is a positive number. So the activation energy is going to be a positive number. And you could just think about the hill, right? This is the activation energy here. It is like being put in, right? It's sort of a positive number. So activation energy should always be a positive number. And again, that's why the negative is here. And again, this line that you get will be negative in terms of the slope value. And those two negatives will turn our activation energy into a positive number. Any questions on that there? Yeah. So this is sort of the Uranus equation, and it's very, it's obviously temperature and energy, but it is typically the one that we use sort of for graphing purposes to sort of graph these things. And just to kind of expand on some of the stuff that we talked about, um, again, that sort of frequency factor and so forth is really that proportion of molecules that do have enough energy really to get up and over that hill to the other side. One way we could kind of assure that is, as we talked about, typically when we do increase the temperature, really what that is doing is adding more energy to everybody, is going to allow more people to, like I said, get up and over that hill to the other side. Because more people have enough energy to do that, that translates to usually us seeing the rate of the reaction increase as well. And obviously vice versa as well. If we decrease the temperature, we're going to basically be removing all that heat and energy from everybody. That's going to result in less molecules really having that right amount of energy to get to the other side. And that's really the activation energy. The activation energy really is the minimum amount of energy required for a reaction to take place. There's really a couple things that need to occur when a reaction takes place. You need to have guys pretty much collide with each other. It has to collide with each other in sort of the right place, sort of the activated place on each of them. But in addition, they need to kind of collide with each other with enough energy, basically, to kick off that reaction. And that's sort of the activation energy. So again, increase in temperature obviously helps that process of when they do collide, we'll get somebody with enough energy to kind of start the reaction. Um, and again, not all collisions, just because some two things kind of run into each other, doesn't always mean that you're going to make a product as a result of that. So those two things are really important in terms of whether or not you would see a product actually being formed, which is you need to make sure that they actually collide with each other, but they do need to collide with each other in the right location and also with a sufficient amount of energy to allow that to occur. And this graph representation here shows us sort of what we've been talking about, and that sort of proportion of molecules that have enough energy to basically that minimum amount of energy to get up and over that hill. We look at a graph of T1, which is the blue line, T2 is the red line, and T2 is higher in temperature. And what we see is at the lower temperature, we really only have about this much proportion of molecules that have enough energy to get up and over to the other side. While when we look at sort of the red or higher temperature, we see a much bigger area of molecules that have sufficient amount of energy to make it up and over to the other side. And again, for those reasons that we just talked about, having that increase in energy, that extra energy going to allow everybody to really make it up and over the hill, basically, to the other side. Just like if you were running up a hill, you had a lot of energy, you would get up there pretty quick. If it's like the 40th hill you ran that day, you probably don't have too much energy left. You're going to probably be regretting it and moving very slowly up the hill. So it's sort of the same idea here. Increasing that temperature gives everybody more energy to get up and over. Decreasing it kind of slows everybody down and their progress. And the effect is obviously a lower or slower rate for that particular